Hi, welcome to my talk, Lies We Tell Ourselves Using TypeScript. It has been a fantastic TypeScript Congress so far. You have seen lots of fantastic speakers, people that I wanted to meet for such a long time, people that I've engaged with on social media and who are the best of the best in TypeScript. And now I need to tell you that I'm sorry. I'm sorry because you had fantastic talks from fantastic speakers, and now I'm going to crush your dreams and destroy your hopes because this is not going to be a fun talk. You know, I've done my fair share of TypeScript development. I've written 2 books about it. One, which is, TypeScript, the good parts. This is how the type system works for JavaScript developers. And the other one, TypeScript Cooker, where we have 100 actual problems that we are going to solve together. And throughout my journey, I always start with this example where TypeScript is absolutely perfect for. I have this JavaScript code. Don't worry about what it does, but it's just JavaScript. The browser executes it. It just doesn't work. There's no error that's being thrown. Nothing tells you what's going wrong. It runs, it doesn't throw any errors, but it does not produce the right results. And for examples like that, TypeScript is fantastic. Because TypeScript, just when I activate it, finds about, 10 errors in 15 lines of code. That's what we're here for. That's TypeScript's purpose. But this is not what I'm talking about today. Today, I talk about the total opposite. I'm going to show you an example that TypeScript is totally happy with. We are just fetching some data from some API and concatenating it with something else. And TypeScript says, well, the types check out. This is good code. It compiles. You can ship it. And it will most likely crash at runtime. At runtime, those things that TypeScript is supposed to prevent. Let's go through the code step by step. The first function fetches data. We call it list entries, and you have two function overloads that define an API for you and your users. If you get a kind of species, then you're getting a promise of species in return. If you're getting a kind of people, then you're getting a promise of people in return. We are accessing the Star Wars API, which is great if you want to do any REST tests. And you have a very tailor-made API so that you actually know what you should get back. Then you have the third function overload, which is the actual function implementation for you. Next, we are fetching data. And since it has some meta information, we are unwrapping it. We are just interested in the results. One thing that is very interesting about this line of code is that we are doing some error handling. So there's one part where we say, well, that result.json call on line 3 might go wrong. So let's better catch that syntax error. What if we don't get any JSON back? Fantastic. 5 lines of code for that function, 3 lines of type information. The next is one-liner. I just formatted a little bit for this slide. Then we are concatenating a promise of an array of people or species to another list of array of people or species. So we're concatenating those two with the push method of an array. And finally, we are calling it. So we are creating a new people array and we are appending species to the people array. All right, this is our program. It's about, 10 real lines of code, a couple of type information. And I want to ask you, if you look at the entire program, do you know what's going wrong? Or do you know what's supposed to go wrong? So, well, I think everything. And where does it go wrong? Everywhere. And when does it go wrong? Yeah, one by one, because we're single threaded. But don't worry, we are going through it step by step. We are now going to look at all our problems. Problem number 1, in chapter 1, a tale of fetch. Let's look at the core of our very first function. If you look at that, it's marvelous. We're just fetching some data from the Star Wars API, and then we are calling result.json. So we have a JSON object and we are unwrapping it. But there's one little tiny lie hidden in line number 3. This type annotation, let data of type meta people, just works because the result.json call returns a promise of any. And you know any. Any is the happy-go-lucky type in TypeScript. Any says, I'm not doing any type checking at all. You, as a developer, you know best. And since we are assigning any to meta of people, things break. Because TypeScript then thinks that you know best, and you know that the result, or that the JSON result of result should be meta people. But this is just done by yourself. No type checker helps you with that problem. And what we're seeing here is TypeScript at its boundaries, where the meta world of your types, that work well together, that you designed how they should be, meets the real world when you have user input, when you have network I/O, when you have stuff from APIs. This is where something from the outside enters your type world, and you need to make sure that those things line up. And TypeScript has a very nice way of showcasing those boundaries, or showing when those boundary problems arise. I like to call that unsafe operations. And we have keywords for that. We have, for example, a type assertion. So instead of doing a type annotation, we can say, well, result.json should be meta people. And this is an explicit type assertion from us where we are bending the type system. The same thing with function is dice, where we say, okay, if I'm getting a number in and it is from 1 to 6, then I know it's of type dice and I can bend the type system. I can say, type system, I know better than you do. Same with assertion signatures. And all those keywords, as in these, for us, signal that we are bending the type system to our will. So if I ask you, what of those two things actually shows better that the type system is being bent a little bit? It's number 2, because you can do a full text search for the keyword as, and you find all the positions, all the places in your code where you're bending the type system to your will. Number 1 is just a type assertion. You're never going to figure out that you're having any on the right-hand side, and it suddenly becomes a matter of people on the left-hand side. So what we want is actually number 2. But the problem is that type annotations with any just work, and nothing keeps us from doing that. TypeScript is totally happy with it. What would be better in that case if result.json wouldn't produce a promise of any, but rather a promise of unknown, because unknown is the cautious sibling of TypeScript. Of any. Unknown is the cautious sibling of any. Unknown tells you, please check everything before proceeding. And we can tell TypeScript to use unknown instead of any, with a little thing called declaration merging. So no interface in TypeScript is ever closed. You can always add new methods to it. This is, first of all, for keeping track of ECMAScript versions, fantastic. Second of all, also for you to patch stuff according to your browser's needs or to your environment's needs. This is how jQuery handles plugins, for example, and how TypeScript works with, the object constructor and whatever. And you can tell TypeScript, the body interface, which is the one interface that our result gets its methods from, has another JSON method of promise unknown. And since it's the last one, since you edit at the last position, this overrides the other one. So you have another function overload that now returns a promise of unknown instead of a promise of any. And if you add those 3 lines of code, then suddenly you're getting an error. You're getting an error, and TypeScript tells you, wait a second, the type unknown is not assignable to the type meta people. Unknown is the cautious type of any. Same set of values, but very cautious. And this is where you need to do extra checks. Either do a type assertion, or maybe use something like sort and make sure that the data you get is actually the data that you're looking for. Cool. Problem 1 found, problem 1 solved. Let's look at problem 2. The theme is dark and full of errors. This one is so interesting. This line of code where we are catching for a syntax error. The developer was very clever because they thought that result.json might throw a syntax error, and they are right. If you don't get any JSON back, it's a syntax error, and then you can catch the error and maybe return an empty array or whatever, use something to mitigate that error. I'm just throwing another error, who cares? But, we want to make sure that we are catching that syntax error. The problem is that in JavaScript, anything can throw everywhere. So errors can happen all the time. And this is why the developer added any to a union. And again, in JavaScript, everything can throw. You can throw the number 2. You can throw undefined. You can throw tantrums like my 2-year-old. Basically, JavaScript and my 2-year-old are the same thing. In JavaScript, everything throws, and I don't know where it's coming from. My son throws tantrums, and I don't know where they're coming from. But anyway, if you look at that line, the little any in the union with a syntax error should tell us that this is what's actually happening. You either have a syntax error or you have any error. Because, just have somewhere syntax error, somewhere type error, or whatever, and your program crashes. So it's true. The statement here is absolutely true. The problem is that if you put any to a union with something else, you are getting any again. The happy-go-lucky type that, deactivates type checking for you. So we are basically catching for any, which means that if you access e.message at this point, that might go wrong. So it just prints undefined now, but what if you do something with the message, like to uppercase, or you send it somewhere that expects a defined value? And you can again solve this with a little compiler flag called unknown in catch clauses, and you do instance of checks later on. So you activate the flag, use unknown in catch variables, then your error is unknown by default. So you don't need to catch for a syntax error or for any or whatever. It's unknown by default. And then you can do checks, instance of checks on syntax error to get to the actual properties of a syntax error. And this is how you mitigate these problems. So problem number 2, error handling, solution, do instance of checks. Problem number 3, the metrics overloaded. Now it gets juicy. Wait a second. Let's look at those function overloads again. We have 3 function overloads. 2 are for the interface, for your users, like kind of species returns promise of species, kind of people returns promise of people. And then you have the broader implementation signature, one that you can actually work with. You get either kind of people, kind species or people, and then you return a people array or a species array, one of those, or array of people or species. Good. The problem here is that if you look at that line of code, the only thing that I return are people. I'm not returning species, but the types tell me that I get species. The code tells me that I just return people. So I can request species in my code, and the type system tells me, well, everything is species, but in reality, I'm just working with people. And if those two types are different, well, then you have a big problem, because then you're accessing properties that don't exist. All right, so let's look at those function overloads in detail. We can split it up. So if you have function overloads, 2 are always for the usage, and the third one is for the implementation. And there are 2 type checks happening. First of all those usage checks check if they are being covered by the implementation. So you can't write anything in the usage section that is not being covered in the implementation section. This is what's happening here. So if I add species and people to kind, then I also need to make sure that the implementation signature takes care about both as well. You either use a union or use a very broad type like string. And the same with the return type, same thing. This is the first type check. The second type check is between the implementation and the function body. So then you look at the implementation signature, and everything you write in the function body will be checked against the implementation signature. So those 2 worlds will be checked, but nothing checks if your implementation actually covers all the usage entries. Nothing checks that. And this is the big problem with function overloads. So first of all, great, you're getting a tailor-made API. The problem is that, well, there's a disconnect between the function body, the implementation signature, and the usage signature, because it's not checked everything. There are just 2 different type checks happening. A solution for that is doing conditional types. Conditional types, you can basically define as the similar API. I'm now having here return type, where I say, well, if I'm getting species, then return species. If I'm getting people, return people. Otherwise, this will never work. Don't use anything else other than species or people. And then I can use generics, use my conditional type, and suddenly I'm getting an error, because conditional types are very complex. The function body can't be validated against the return type of a conditional type or the conditional return type. So I'm getting an error where I say people or species array is not assignable to return of t. Now I need to do extra checks. Now I need to do type assertions. Now I need to do unsafe operations. Now I highlight the potential problem in my code. I'm getting an error, and this is what we are here for. Now to my favorite, chapter 4, the unexpected virtue of ignorance. Let's look at this single line of code and the type signature around it. So I'm getting 2 parameters. One is an array of people or species. The other one is a promise of an array of people or species. Then I concatenate the 2 of them. Fantastic. That's all that's happening. I just take 2 arrays, concatenate them. Beautiful. Then I'm creating a people array. And then I'm calling await append entries of list and list entries of species. So I'm concatenating a people array with a species array. What's the type of list after append entries? It's still people. The type of list is still people, even though I'm adding species to the array. So this is, I have no words for that. I'm so sorry. I have no words for that, just animations. But this is beautiful. This is such a beautiful error, and it annoys me so much that it happens. But what's happening here is the following, that all the contracts are fulfilled. So if I'm having a list, which is an array of species or people, then I can add a people array to it. And if I have another list of array of people, then I can add a species array to it. The problem is that the original list is being mutated, and in TypeScript, nothing exists to highlight those mutations from, for example, arrays or whatever. So the type doesn't change afterwards, and this is a problem. But there's another solution for that. If you are encountering things like this, always add generics. Generics are beautiful because generics have a very fantastic feature, which is that they lock your type into something concrete. So what I'm doing here now is that instead of taking the broad type of people or species, I'm taking a generic type parameter t, which extends an array of people or species. Then I have a list of t and I have a promise of t. I do the same thing. It's just the same code. But now when I create a list of people and I put that list into append entries, TypeScript locks t to array of people. So it locks it to the subset. It's not taking the broader set anymore. It locks it to the subset. And the moment it locks it to the subset of array of people or species, the moment it locks it to that subset, it figures out that what I'm getting here is not of the same type as list. So it tells me, wait a second, the argument of type promise species promise of species is not assignable to the parameter type of promise of people, because list defines the concrete type. This is an error. This is what we're here for. Now we can act. Okay, everything mitigated, every potential problem now has a solution. Please enter the final chapter. Lies, damn lies, and TypeScript. So far, we found 4 problems and we found 4 mitigations. We used declaration merging to patch the assumptions made by the standard library. We use instance objects and unknown to narrow down error types. Great. We use conditional types instead of function overloads to highlight unsafe operations. And 4th, beautiful, we use generics to narrow down to specifics. 4 problems, 4 solutions. And all of the solutions just have more lies. I'm so sorry. I just told you more lies. First of all, interface declaration merging is fantastic. You can extend the global namespace and add more properties to it if your software needs it, if your libraries need it. If you have Google Analytics in the window interface, well, then you can just add it to the window interface. That's what you do. It's great unless you are defining a new interface that you accidentally merge with the global, like form data here. This has happened to so many people already. I'm constantly getting messages from people on Twitter or Mastodon or wherever, where they say, I had exactly the same problem because I was defining my form data with the interface form data, and guess what? It's a global, and nothing tells me that it's a global. And suddenly you're getting more methods like .get, .set. Where is this coming from? Well, it's coming from a global form data interface that I accidentally merged with. So declaration merging is great unless you accidentally merge with globals. Now something that makes my toenails go up. It's hilarious. I have 2 classes, class A and class B. Both have a number property. One is called A, the other one is called B. And then I have a do something function where I'm getting a union of A or B. So it's either A or it's B. And I'm doing instance objects. So I'm doing P instance of A, then it should be A. So I'm logging out A. And in the else branch, it's B. So TypeScript tells me that it's B, and I'm logging out P.B. Good. So this is how it's supposed to work. Beautiful. So now I can create new instances of A, new instances of B. I'm having instance objects. Everything is as it should be. And then you realize TypeScript has a structural type system, and that you can enter an object that just looks like an instance of A, and that it will type check. So do something with this object A42 type checks. But if this object goes into the do something function, it will not be an instance of A. It will not be an instance because it's not being created with the new keyword. It's just something that looks similar to an instance of A, and TypeScript is happy with that. So this instance of A checks falls through, you're in the else branch, TypeScript thinks you're B, but in reality you are an object like A. So yeah, instance of checks are great until you realize TypeScript is structurally typed. Yeah, third problem, conditional types are great unless... I'm so sorry. Seriously, I'm so sorry if you look at that. I have no clue what it does. From the creators of regular expressions comes the sequel nobody asked for. No, I'm so sorry. This here is, I guess it's about currying function overloads. I don't know. I've written this type, so it's done by myself, and I couldn't tell you what it does because just a week ago I totally forgot what I did. I've written a book about it, so this is part of my book to explain what's going on. But so if you use conditional types, know about their complexity. They are great because you can do a lot of things with it. They are very powerful. It's amazing what you can do with it, but they require extra documentation and extra care. And you're not here to work for the latest and greatest and for the most code voodoo that you can do. There's no magic in coding. You need to work with people. You need to work with yourself, or you need to work with your colleagues. And if this goes into your code base, double check what's going on there, document everything, write test cases for that. You can write type test cases. You can do that. Make sure that everything in here is documented and available, and it stands the test of time. So yeah, conditional types are great unless you figure out they are actually quite complex. And last but not least, generics are great until you explicitly make the set right as they should be. You are always able to explicitly annotate the generic type parameter, and then everything goes boom again. So yeah, 4 problems, 4 solutions, 4 more problems. Let's go for the epilogue. All right, folks, I told you, I'm sorry. This was not the fun talk. This was just problems and more problems and lies above lies above lies above lies. And I'm very sorry for that. And you might think, I've written 2 books on TypeScript. I'm doing consulting on TypeScript. I'm working with lots of teams on TypeScript. And I'm creating a TypeScript runtime, like Deno, but internally. What do I think of TypeScript? What do I think of TypeScript after finding all those big problems? And I have to say, I fucking love TypeScript. Seriously. It's still the second best language I had the pleasure to work with. It's so much fun and it makes me so productive. And you can't argue with that. TypeScript makes you productive. This talk is not called lies that TypeScript tells us. This talk is called the lies we tell ourselves using TypeScript. And there are lots of lies that we tell ourselves. We tell ourselves the lie that TypeScript is 100% type safe. We are telling ourselves the lie that we can forget about our code because TypeScript has our back. And maybe we are telling ourselves the biggest lie, that we think that we are here to write code. And I don't think so. I don't think that we are here to write code. I think we as software engineers are here to make decisions, and we're here to validate the trade-offs of every decision that we are doing. TypeScript is just a tool in the box. The code that you write and everything that you get, for example, from Copilot or Stack Overflow or wherever, if you put it in your code base, you make the decision that this code is good enough to be put in your code base. And this is what your main task should be about. Tools can just help you make decisions, but you still need to know what's happening underneath. And you know who's really good at making those decisions and trade-offs? The TypeScript team. This is one page from the wiki on GitHub, which defines goals and non-goals. And I think the non-goals are very interesting because there's one line that basically tells you the reason for everything that you just saw. A non-goal is to apply a sound or provably correct type system. Instead, they want to strike a balance between correctness and productivity. And all those little errors that you just saw come from exactly that line. They put productivity first. And with that, there might be a couple of patches where, things might not end up as they should be. But still, you make the decision to put that line in your code. So you are the one responsible for that, not TypeScript. You just need to know about the trade-off. And there's a big trade-off in TypeScript that, stuff might not be provably correct in the type system. And you might say, well, why do they even bother if they're not making it perfectly correct? Because the main goal was always to make developers productive. I gave the same talk in front of 4,000 people at the VIA Developers World Congress, and I asked two questions to the audience. Question number one was, who is using TypeScript in a room with 4,000 people? Over 90% were raising their hands. And then I asked them, does anybody remember a type system called Flow? And it was 3 people. 3 people in 4,000 remember a type system called Flow, which was Facebook's answer to TypeScript, very similar in syntax, very similar in features, but the Flow folks had the goal of having a provably correct type system and thus killing productivity for everything outside React. We see what has prevailed over time. As much as I like Flow and I know people from the Flow team, I know what they worked on and how they approach things. It's a beautiful type system. But this little decision to put productivity first is what made TypeScript so popular in the end. And this is the point of my talk. The point of my talk is that if you use TypeScript, please love it as much as I do, because I seriously love TypeScript and it's so great to work with. But be aware of the trade-off that you're making. Be aware that the type system might work differently than you expected, and it's still your duty to learn it. It doesn't take away the responsibility of learning a programming language just because you get such excellent tooling. And this leads me to the one learning that I want to transport you, which is the one thing that you should take home. Be pragmatic and be aware. Choose what works best for you and your team. And if you don't have a team, well, you have always future you that you need to work with. You'll never code alone. Don't listen to dogmatic advice. It's so easy to make, I guess it's TikTok where you have those shorties, or a tweet or whatever that gives you this one beautiful, fantastic advice that kills everything else. But then, it's just another decision that somebody else made for you. Don't listen to dogmatic advice. Always question everything. Validate it against what you need to do. Be pragmatic, be aware, make decisions, well-informed. And with that, I want to say thank you very much for listening to me. Thank you very much for meeting me. I hope you had as much fun as I had. Thank you very much.